In this video, we're going to look at a binary search algorithm. So a binary search algorithm can be very efficient because a binary search algorithm, every time it goes through a loop, eliminates half of the possibilities when it searches the loop. For a binary search element to work, the elements in the array have to already be ordered. So we have to have sorted them already. And we're going to see how to sort in an upcoming video. Okay, so for this example, we're going to assume that the array is already in ascending order. So here's an example array, 2, 4, 7, 10, already sorted from lowest to highest. So how does a binary search work? Well, a binary search first takes your entire array and looks for the middle element, okay, to see if it matches the thing you're searching for. Let's pretend we're searching for a 7 in this case. It looks at 50. Is 50 equal to 7? Nope. But 50 is bigger than 7, which eliminates 50, but it also eliminates everything to the right of 50. So I just cut the size of the array that I have to search in half. Okay, so now 45, so it wasn't 50, it wasn't 59, 60, 66, or any of these. So now 45 is the largest element. I know I need to search between 2 and 45. So I find the center element again, and it's 10. Is 10 equal to 7? That's what we're searching for, is a 7. No, 10's not equal to 7. So it's bigger than 7, which means I can eliminate everything to the right of 10. So we eliminated 50 to this, so I get rid of 10, 11, and 45. Now I'm down to 2, 4, and 7. Okay, I look at the middle element. Is the middle element equal to what I'm looking for? Nope. But it's smaller than what I'm looking for, so I can eliminate the 2 and the 4, and all I'm left with is a 7, which will be the middle element. I found it. Okay, so it took me 3 times through that process to find the 7. So let's take a look at this. The book manufacturer actually has a pretty decent simulation of this. It's one of the better ones I've seen. So this lets us generate, I generated an array with 15 elements in it, 8, 28, 13. So it's got numbers from 8 to 93. And I told it I want to look for a 92. Okay, so here's the algorithm and how it works.
Since 92 is greater than 56, continue to search right.
All right, I'm turning off the sound. Our lowest index number here is 0. Our highest index is 14. Okay, we average those two together to get 7, and that tells us the middle index. Okay, we're looking for a 92. Okay, 56 is not 92, and it's smaller than 92, which means we can eliminate everything between 0 and 56, which means we can make 63 our new low number. Okay, so we only need to search what's left after we eliminate all these things. Okay, so if we hit next, our new lowest number becomes index 8. Okay, 0 up to 8. Okay, our highest index number is still 14. 8 and 14 are 22. The average is 11. And one of the questions people often have here, well, what if the number comes out to a 0.5 when you divide by 2? Well, we just cross off the 0.5. It really doesn't matter. We can do integer division there when we divide by 2. It won't hurt a thing. All right, so it's 87. Okay, that is not 92. It's smaller than 92, so we can eliminate everything from 87 down to the left. We've already eliminated all this stuff. So our list now is down to 88, 92, and 93. So we hit next. So 88 becomes our low. The index 12 is our lowest index, and the 14 is our highest index. And our middle index is the average of those two, which is 13. 92 matches. So a key was found with the index 13. So 1, 2, third try. As opposed to a sequential search where if we were looking for 92, our loop would have had to run 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 times. Okay, This one, the loop had to run 3 times. That's what makes it efficient, as long as the items are sorted. Now, that becomes an issue because sorting will take some processor time too, right? So when is this the best way to do it? And there's a whole field of mathematics we can look at to determine when it's efficient. With a very small array of numbers, it probably isn't efficient to sort them first and then go through this binary search. A sequential search would probably be quicker. But if I had 1 million numbers and I wanted to sequential search them, that would take on average 500,000 iterations before we found the number. And sometimes it may take 1 million iterations. But a binary search would be highly efficient. So the time it takes to sort them first would make it worthwhile. Okay. So binary search, the bigger the array, the bigger the number of items in the array, probably the more efficient it would be. With very small arrays, just a sequential search could be more efficient. Okay. But let's look at this with code. Let's actually look at the code that does this and see how it works. So here is something very similar to what we saw in the sequential search video, except I'm calling binary search this time and passing it the array. The only difference is I have the array sorted already, and we'll talk about sorting in an upcoming video, so we can actually sort this with an algorithm. But I'm starting with one that is already sorted because that is the caveat to using a binary search, that it has to go through this sorting process first. Okay, so we pass in the array and the thing that we're looking for in the array. And the first thing it does is sets the high index number to the length of the index, length of the array -1, and the low index number to 0. And basically what we're looking for is we're making those indexes get closer and closer. Okay, so as long as the high is greater than the low, we're going to keep doing this. If we get to the spot where the high index and the low index are the same and we haven't found it, it's not in there. Okay. So we average those 2 index numbers together for the high and low. I told you about that. And we divide by 2. Again, that's integer division. So if it comes out to a 0.5, it just gets truncated. It's not a big deal in this case. We consider that the middle number. And then we look to see if the thing we're searching for is equal to that number. We saw that happen in the simulation. If it was less than that, then we set the new high value to the middle -1 because we've eliminated the middle and we've eliminated everything higher than that. But if it wasn't less than that, we check to actually see if it matches. Well, did that key actually match? A lot of times you see this test first before that one in these algorithms. Okay, if it matched, we'll return that index number. Otherwise, we'll set the low value to the middle +1 and eliminate all those low numbers. So when we repeat that as many times as we need to, I would trace through this, and we could watch it work, and feel free to do that with your debugger if you would like to do it. But what we would see happening is this exact simulation that we just did. So I do like this simulation. It does a good job of showing. I wish it would cross out the numbers that get eliminated, but it doesn't. But it shows you the process of changing these low and high values till they get closer and closer together, and we narrow into the number we're looking for. If we never find the number we're looking for, so let's reset this, and I'm going to look for, there's no 21 in here, so I'll put a 21. I can say next. Okay, 21 is less than 32, so we eliminate all the top numbers. And we go through here. 26 is greater than 21, so we eliminate all these numbers. 23 is greater than 21. The middle doesn't count. Now high is equal to mid, and it still doesn't match, so we know we're done. And it returns a negative number in this case. Some algorithms will return a negative number. Ours was returning a -1. but the result's the same. It didn't find the number. All right, so that's a binary search. Here's binary search code written in Java. Please take the time to run through this and look at it and understand it. These are the kinds of things that come up if you're going to get a programming job. They're going to ask you to at least describe a binary search sometimes in your interview. And it's a good algorithm to know because it's highly, highly efficient.